Okay, so today we get to Reconstruction. And let me just remind you what we finished with last time. So last time we talked about V4 of holographic entanglement entropy, which is the quantum extremal surface formula. So if we're given region R on the boundary, this is computed by the generalized entropy of a quantum extremal surface, chi R, where quantum extremal means it's a stationary point of the generalized entropy functional. So delta S gen, delta SA equals 0, where SA is any normal to chi R. So this is and of course S gen is the generalized area plus the von Neumann entropy on one side of this surface chi R. Okay, and we define the entanglement wedge as the domain of dependence of the homology hypersurface of chi R. So picture, this is the region R, this is chi R. So on this time slice, this is HR. And then if we look at a time-dependent version, this is V of R, this is chi R, and the entanglement wedge is everything in here. And R is some region here, like that. Okay, so that's just to jog your memory. And we talked about a bunch of properties of quantum extremal surfaces. For example, the fact that we don't have complementary recovery. This is very important. So two very important things I want you to remember about quantum extremal surfaces. Important facts. So the first is that chi R is not necessarily the same as chi R bar. So that's just telling us that there's no complementary recovery necessarily in the case of quantum extremal surfaces. Your bulk state is mixed. And then the second property that's important is that chi R depends on the state of the quantum fields in the bulk. Which is not true of the classical extremal surface. So the classical extremal surface just depends on the area. This also depends on the von Neumann entropy of the bulk quantum fields.
So this is the so-called state dependence.
This is one of the things we call state dependence. Yeah, yeah.
But it doesn't. So originally, when it had state dependence, it seemed to violate the linearity of everything.
Yes.
Right.
It depends on different kinds of state dependence, right? This is just a statement about the part of the bulk that computes the von Neumann entropy. The von Neumann entropy is not a linear observable, so we don't have to worry about that at this point. State dependence does come in, of course, when we talk about the black hole information paradox and reconstruction behind the horizon. And time permitting, I may be able to say a little bit about that in the context of quantum extremal surfaces. Yeah.
It's not by the biologically we expect that the state of the CFT describes both the geometry and the state of the quantum in the back. So it's like we added another information.
You mean when you don't have complementary recovery?
No, when you said that it depends on the state. I mean,
yes.
We also, it should have been also in the third formula, it was just ordered to be Newton or something.
Good. So the chi R always depends on the state of the CFT, and of course you could say it depends on the state of the bulk in the sense that, classically, in the sense that it depends on the bulk geometry. The main difference here is that it also depends on the matter content. Even if you're in a situation, which we will work with in a moment, where you have a fixed geometry and you're considering very, very small perturbations on it of the quantum fields, so you can basically treat the geometry as not changing, but you'll still find that the quantum extremal surface can change. So for example, if we're working purely classically, then that's not going to happen.
I like version 3.
Unlike, sorry?
I like the
previous
formula.
version. Yeah, that's right, exactly. Yeah.
And another one, this formula was checked or verified for specific cases, like
Of the what?
the version 4 was verified in some
Yeah.
specific cases.
So version 4 is to all 100% here. So this is time dependent, meaning covariant, and to all orders in G. All right, good. So now that we finally have this definition in a version which we can say is more or less hopefully final, then we can ask, all right, what about reconstruction? I didn't title this talk holographic entanglement entropy. I titled it reconstruction and complexity. So now part of the way through the third lecture, we're getting to reconstruction. So it helps to begin with to work in this Faulkner-Lefkowitz-Maldacena case, where we're actually forgetting about the back reaction, and we're working to first subleading order in quantum corrections. Meaning we have, so temporarily, we'll include back reaction momentarily, but for now, we're going to work in the limit where we have a fixed classical metric, and we're including quantum fields propagating on it, but we're not worrying about the back reaction of those quantum fields. This is the limit where we can work with this, with the Faulkner-Lefkowitz-Maldacena proposal for holographic entanglement entropy, where we still have an ordinary classical extremal surface, but we're including the von Neumann entropy of quantum fields on one side of it. So we're going to work with this for a little bit, and then we're going to generalize. Okay, so we have some. We're going to have some metrics, so we're going to call this classical metric GAB on our spacetime manifold M. And we have some state of the quantum fields, which we'll call the quantum fields in a state rho HR, where HR is the homology hypersurface. Of XR, which is the HRT surface of the boundary region R. Okay, so now, draw a picture here, time slice, R, XR, rho HR. Now what we're interested in doing is we're interested in turning on some operator here. And we'd like to then reconstruct that operator in the dual CFT. That's what we mean by reconstruction. So I'm going to turn on some local operator in the bulk. Call it X. So at this level, we don't have to worry yet about gravitational addressing. Sorry? Yeah, that's right. There's no back reaction yet. We can, so in general, I'm not going to worry a lot about gravitational addressing. I'm always going to adopt a situation where adopt a convention where if we need to gravitational address an operator, we fire a geodesic towards the extremal surface. And that's what I'm going to be using with addressing. An example of a local operator. I mean, any operator which is localized, okay, approximately localized to a point, any local field that you want to turn on, localized to some very, very small region, and then we take the limit as that region goes to, as that region goes to 0.
So, energy management.
So, sorry?
The energy management.
Yeah, for example, thank you, yeah.
Why don't you first consider the classical fields? So you add to the matrix some fields,
Sure.
and the classical fields will also have some entropy.
Well, the classical fields we can get just by, if we just have the solution, the metric, and the equations of motion, we can reverse engineer TAB with the classical fields. So it's sort of less interesting than trying to reconstruct the quantum fields. You can talk about reconstruction of the classical fields, but again, it's essentially boils down to reconstruction of the metric. It's a little bit different, but once we have quantum fields, it becomes a little bit more non-trivial.
The question of whether there is or not back reaction does not relate to whether these are classical or quantum fields.
It will. So just bear with me here. It's going to, so what you're expressing are intuitions that we all had before 2019. Or, I would say that's not entirely fair, before 2017 really. But these intuitions they're very fair, but they turn out to not be correct. So just bear with me here while we first talk about this limit, and then we're going to see how things dramatically change once we talk about quantum extremal surfaces instead of classical extremal surfaces and include back reaction. Okay, so the fact that we turn on some operator, so that results in a change in the state of the bulk quantum fields. Right, we've done something to it. So now we have some state sigma HR in this homology, on this homology hypersurface. So we've done some side modification, and we have a new state. And what reconstruction is going to mean for us is that the CFT, we are able to tell the difference between rho of HR and sigma of HR purely from CFT quantities that are localized to R. If you can distinguish between those two, even when they're related by something as simple as turning on a very low energy local operator, then we can reconstruct operators inside of the entanglement wedge. So the goal will be to figure out if there is a way for the CFT to distinguish between sigma HR and rho HR. And so the way that, and I should say in particular, we're most interested in turning on this operator behind the causal wedge, because we can reconstruct, you can figure out that there's this protocol called HKLL for doing reconstruction within the causal wedge, and so we're most interested in seeing, can we actually reconstruct the full entanglement wedge? If we turn on this operator somewhere behind the causal wedge, let's say the causal wedge looks like this, can we always tell from CFT quantities defined purely on R if we have sigma R or if we have rho HR, so sigma HR or rho HR? That's our task here with reconstruction. So that means that we have to find a good way to distinguish between states. And there are many good ways of distinguishing between states. We can talk about things like trace distance, other quantities. For us, it will turn out to be most useful to talk about the relative entropy, which is one measure, one state distinguishing measure. So the relative entropy is defined for any two quantum states. It's really most useful when you're talking about mixed states. Okay. So for any two density matrices, rho and sigma. So this is defined independently, bulk or boundary, just an ordinary, just some ordinary quantum fields here, quantum states here. This is trace of rho log rho minus trace of rho log sigma, which we can of course also write, this is just minus of S of rho. And this is the expectation value of this operator K sigma, which is the modular Hamiltonian of sigma. So K sigma minus log sigma is the modular Hamiltonian of sigma. And even though I won't have a lot of time to talk about the modular Hamiltonian, it's proven to be an incredibly useful quantity in AdS CFT. So it was used in many proofs of reconstruction and understanding various fine-grained properties of AdS CFT. So again, even though I won't get a chance to talk about it too much, I really encourage you to read up on the modular Hamiltonian. It's a very valuable quantity to know about.
Just one question. What does it mean to turn on a local operator? Are you acting with some operator on the state? What does it mean to turn on a local operator?
Well, yeah, you're acting with some operator on the state. It's just, it's localized to a particular point, or if you want to, if you don't like local operators in quantum gravity, you have some Wilson line connecting it to the extremal surface. Yeah, you turn on this operator, it means you act with it on the quantum state. So now you've changed the state. Yeah.
I suppose the relative entropy finite?
Well, it depends on, if you're talking about pure states, then not necessarily. That's the problem. That's why it's more useful as a measure of distinguishability from mixed states. So for pure states, this thing can be divergent, so it's not great for telling you how different two pure states are, but it's pretty good for telling you how different two mixed states are. So we'll mostly use this in the context where we're talking about a subregion and we want to know how much you can reconstruct from it. So that we're talking about a mixed state, some density matrix on that subregion.
It's not guaranteed that it's finite. You have to check it case by case.
Well, yeah, I mean, I think it's pretty much, I want to say it's, I don't remember 100%, but I want to say it's almost never finite when you have two pure states here. But when you have two mixed states, you're good.
Yeah. Mixed state can be continuously deformed to a pure state.
That's right, so it can get progressively, larger. It's just, it's not well, it's not super well defined and not super well behaved for pure states. So it's a distinguishability measure. It's very useful as long as you're not dealing with pure states, and then there are probably better ways to distinguish them, like the trace distance. Okay, so why is this a good distinguishability measure? Well, for one, it's going to be 0 if and only if these two, or so only if these two are the same state. So that's very, very useful. Doesn't even only if. So that's already said, okay, no, if this is 0, then we have the same state. That's a good distinguishability measure. There's a sense in which it gets progressively larger. There's a relation between this and the trace distance, although it's possible to have large trace distance and small relative entropy. So it's all about which distinguishability you want. But for us, it's important that this thing is going to be 0 if those two are the same. So in other words, if the CFT can't distinguish, if we want to ask if the CFT can distinguish between these two, and we know they're different in the bulk, so we'd like to make sure that something like the relative entropy between them, as computed from the CFT, is not 0. As long as it's not 0, then we say, okay, then we know that there's some way of distinguishing between them in the CFT. From CFT quantities that are localized purely to operator. And this was shown by Jafris, Lefkowitz, Maldacena, and Sue. I want to say this was in 2015, maybe 2016, early 2016, I want to say 15, where they showed something very nice here. So this is only to first subleading correction. So this is the Faulkner-Lefkowitz-Maldacena limit. But this is the limit we're working in for the moment. And they showed that the relative entropy between rho HR and sigma HR is equal to the relative entropy of rho R, the CFT state on R, and sigma R, where sigma R is the reduced density matrix on R, and sigma, reduced from sigma, where sigma is the CFT state that's dual to this bulk with that operator turned on. So here, so we say sigma is the CFT state with AdS turned on. So let me explain this a little bit more. We turn on this operator here. We say we don't know for a fact that the entanglement wedge is reconstructible, but we've done something in the bulk and we expect that it has a dual in the CFT. So we say, okay, well, the full CFT state should know about that. So that's sigma. And then we say, is it possible that sigma R, sigma reduced to the region R, actually knows about this? And what JLMS showed is that yes, it does. This is first subleading order in G, so there are corrections of order G here. But yeah, so what they showed is that this quantity here, which is only defined on the region R, and this quantity, which is only defined on the region R, in other words, this is defined purely on the region R in the CFT, this can tell that rho HR and sigma HR are not the same. Yeah?
This is neglecting back reaction.
There's no back reaction. Yeah.
So the wedge does not change upon...
The wedge does not change, no. We'll get there soon. Yeah.
And what's surprising is that phi of x can be outside
Of the causal wedge.
In terms of outside of the causal wedge.
Yes.
So So the attempts to just construct this Calvin equation for motion.
Yeah, so if you, that attempts to, if using equations of motion, the best you can do is get up to the causal wedge, and then this thing is behind it. And how do we reconstruct it? Well, I'll say a few words about that. But the point is that this tells us that it is accessible. The CFT can tell that something has changed. The CFT on R can tell that something has changed in this causal shadow region. Now, I just want to emphasize that the causal wedge is kind of an avatar for the black hole exterior when you have a black hole. But if you have the full boundary and you have a black hole, the causal wedge is literally the black hole exterior. This is like a toy model of a black hole, where this is the black hole interior region and this is the black hole exterior. And essentially what this tells us is that the entanglement wedge can be reconstructed in AdS CFT, even including the regions that lie behind the black hole horizon. So this is a very powerful statement here. And in fact, JLMS didn't actually say that this means you can reconstruct. That was an argument that I'll tell you about now that was made by Don, Carlo, and Wall. But it really heavily relied on the relative entropy and the fact that we have this distinguishability measure that can distinguish between the states in the bulk where one has this turned on and one does not. Now, I'll just say a couple of, actually, before I get into reconstruction, let me say just a couple of words about it. So one of the reasons I say that the modular Hamiltonian is very useful is if you want to actually execute a reconstruction protocol that is not just to say it's reconstructible, but to actually have something constructed, then there is such a thing. It's Faulkner and Lefkowitz at this order. So at the order where we're first updating correction in G. So Faulkner and Lefkowitz wrote an actual constructed algorithm for reconstructing this region here between these two. And what they used was, it's called modular flow. It's sort of similar to how we do the causal wedge reconstruction, where you could say we sort of flow with the regular equations of motion inwards. But here instead they flowed with the modular Hamiltonian. So they used this quantity to essentially evolve in some sort of non-local sense, evolve to get this region here. I'm not giving you a lot of information about it, but I'm giving you enough that you can go ahead and then read this paper. So this is Faulkner Lefkowitz. I want to say this was from 2016, but don't take me on faith on that. I think it's either 2015 or 2016. Yeah.
Can you turn this into a dynamical picture where phi moves along some like a velocity trajectory in the bulk, and then if you see that something special happens as it crosses the region, the area between the causal wedge and the entanglement wedge?
Nothing special happens. The causal wedge is not a special region of space-time locally. So the causal wedge is it's some place where it's like the event horizon of a black hole. You can't tell when you've crossed it. So we don't expect that something special happens when you've crossed the event, this causal wedge. The bulk doesn't see anything special. Now, I'm going to talk probably the last half hour today about what is different between different types of reconstruction in different parts of the bulk. So I think maybe this is what you're trying to get at, that there seems to be something qualitatively different. It seems that reconstruction should somehow be easier in the causal wedge than in the rest, in the entanglement wedge. And I'm going to ask you to hold on to that question until the last half hour when we'll talk about that. Questions? Yeah.
In the language of information theory, is it not that you can go from sigma r to sigma hr using a quantum channel?
That's literally the next thing I was going to talk about. Thank you. Good segue. So, how do we actually know we can do reconstruction here? Okay, so Don Carlo Wall. So this is basically, what you just said is basically what Don Carlo and Wall showed. So there's a theorem, essentially, that you can use that tells you that going from JLMS, leave this up here, just leave this JLMS up here. So going from the JLMS means that if rho HR equals sigma HR, this tells you that the relative entropy between rho R and sigma R is 0, since, right, that's by JLMS, which tells you that these two are going to be the same up to subleading corrections. And from this, there's a theorem that tells you that there exists a quantum channel that does exactly what you just said. So a quantum channel is a completely positive trace preserving map. So it exists a quantum channel. Completely positive trace preserving map. I'm going to call it N. So N goes from density matrices on, let's see.
You will define a quantum channel,
Yeah, so quantum channel is a completely positive trace preserving map.
not a unitary map.
Not a unitary map, yeah. For example, the Hawking, sorry.
A unitary map is a quantum
A
channel.
unitary map is an example of a quantum channel, but for example, the Hawking evaporation process can be modeled by a quantum channel where you start with a pure state and end up with a mixed state. So it's not necessarily unitary. So completely positive trace preserving. I can write this out. It seems that there's sufficient confusion on this. I should just write it out. Okay. So
It's a map of the Hilbert space.
it's what? Sorry.
It's a map of,
It's map on so it's from density matrices on the Hilbert space to density matrices in a different Hilbert space. Yeah. I guess I don't like to say it's a map on the Hilbert space because that implies it takes pure states. So yeah.
so could you give a simple example?
A simple, well, I mean, a unitary map is a simple example of a trace preserving
Too
map.
simple, because
Well,
you wouldn't
I mean,
call it a unitary map.
Well, the Hawking evaporation process, where you start out with some pure state in the infinite past, and then this maps to the thermal state on a much larger Hilbert space. This is an example of a completely positive trace preserving map. Well, so we don't want what you don't want this to do is to give you you don't want it to start giving you negative amplitudes for things that have positive amplitudes to begin with. So that's the completely positive part. Trace preserving means that you're going to go from a density matrix to a density matrix and not to something that doesn't have trace form. So it's basically, it's the most general map we have that's going to preserve very basic things we want to be true about the system. Yeah.
What's the difference between positive and completely positive?
I believe, I'm going to have to get back to you on that one. Yeah. Okay. Let me just make one brief comment before I actually write this out, given that I've already paused. It's very important.
For example, the so-called dollar matrix that Hawking discussed.
Yes,
is
yeah.
an example of that.
Yes, exactly. That's right.
That's perhaps the simplest
Yes.
relevant example.
Yes, yeah, that's right. Yeah, yeah. So I want to make a brief comment before I continue, since I've already paused, which is that it's very important for us that the state sigma HR came about from acting with some small perturbation on the state. Because for this limit to be valid, where there's no back reaction, we have to be working with a small perturbation. If it's low energy operator, local operator, not something that's going to totally change the geometry at first subleading order. So we don't want to create a black hole in the bulk by acting with some very heavy operator here. So in particular, that means that we're interested in this whole statement, all the story I'm telling you, the whole story is going to be valid for a subspace. We're going to be interested in a subspace of states or density matrices, which are some low energy perturbations of our original state. So it's important for us to stay within this subset, within the subspace. And there's a term for this that comes from the the quantum information side of this, which is called code subspace. So when we want to do reconstruction, for now we've defined the code subspace. The code subspace is the set of states that are related to one another with the small, low energy perturbations. We're going to be talking more about code subspaces, and they're going to be more subtle when we go to back reaction, but for the moment it's just this very simple thing. We have a fixed metric. We don't want to worry about leading order back reaction, so we're talking about the very low energy perturbations to this state. Okay, so this quantum channel is going to be going from density matrices in this on this code subspace. So this is this code subspace we're defining in the CFT. We can also define it in the bulk if you like. And this is going to go to density matrices on the Hilbert space of HR. So this is essentially a map between the sets of states that we have that we're interested in the CFT and in the bulk. And you're guaranteed that this quantum channel acting on rho r, so there exists a quantum channel like this, that when it acts on rho r, it gives you rho hr. So this was proved by Dom, Harlow, and Wall in this case where we are working to leading order, to the first sub leading order in quantum corrections.
What was proved?
Sorry?
What specifically is proved?
So they proved that if you start out with this package star with JLMS essentially, they proved that there exists a quantum channel that will do this for you, which essentially tells you that you have a map between the states in the CFT and the states in the bulk in this code subspace. So this is essentially reconstruction. Right? This is what we were hoping
They
for.
prove the existence, but they don't give an explicit.
That's right. They do not. This is not constructive. The constructive
Just an
proof.
existence proof.
Yeah. The construction was given by Faulkner and Lefkowitz, which is it's a very different type of argument from this. Although they sort of borrow some pieces of it, but this is a much more quantum information theoretic argument. That's sort of a more quantum field theoretic algebraic argument over there. They're fairly complementary.
Netta, is it not true that under quantum channel the relative entropy is not the same, but rather there is an inequality generically? So that after the quantum channel, the relative entropy will be smaller than the overall.
Right, but here we are given, the fact that we are given that this is an actual equality is what allows them to then make this statement at the end.
But why is it called a channel?
It's called a channel for, well, it's sort of the most general quantum operation you can do to map between quantum systems, in a sense. I guess I've seen it, you could do it, you have a quantum algorithm, if you want, which is more general and isn't required to be completely positive and trace preserving, so that's kind of the most general thing you could have. A channel, it's called a channel it sort of is inherited from this language of quantum error correction, where you might want to send information from one place to another. And this is related to this whole treatment of AdS CFT as a quantum error correcting code, where we say the map between the bulk and the boundary is a quantum error correcting code, which means that you have some quantum information, you'd like to convey it to someone else, and you'd like to protect it from erasures, so you send it via a quantum channel, a quantum error correcting quantum channel, because you need to somehow encode multiple copies of the state, get around no cloning. And that's essentially where this comes from, and in general where it comes from in the context of quantum error correction, and also why it shows up here. So in the interest of talking about complexity, I've decided to not discuss the quantum error correcting code story of AdS CFT, but it is there in the background of all of this. That AdS CFT can be modeled as a quantum code, that the bulk to boundary map can be modeled as a quantum code. And this quantum channel is essentially is the map that you're going to use from one to the other. Okay. Any other questions?
So this theorem doesn't give you a way of actually doing this. Or do you
I mean, what is actually doing? What do you mean? What is actually doing this? I mean, Faulkner and Lefkowitz gave this nice construction.
Yeah.
So we do have a constructive argument for this. But this, of course, is all within all to first subleading order of G. And so we would like to ask what happens when you go to further subleading orders.
So I lost the context. It's just AdS, CFT that is being considered as asymptotically AdS.
Asymptotically AdS. You can even talk about asymptotically locally AdS space times. But we are not considering distiller here by any means.
No,
Yeah.
but it includes black holes.
Absolutely. Oh, okay. Not yet. You could say we include black holes in the sense that there could be a black hole in this space-time, but we can't create a black hole at this point because we're restricting ourselves to low energy perturbations on top of some given geometry. So this is actually, thank you, is a nice segue for me for justifying why we might want to keep working to higher orders and include back reaction. You want to be able to talk about black holes. We want to talk about the black hole interior. We want to talk about creating black holes. We want to talk about reconstructing black hole microstates. And all of that is going to require us to be able to talk about subleading orders and back reaction. So that's our next task. Okay. Further, let's call it back reaction. Once we include back reaction, we have to use the quantum extremal surface formula. So XR is going to change to chi R. And here, be monsters. Okay, so let's consider the JLMS statement. Right, this is the JLMS statement. Now, we can look at this and already start to get worried in the context of quantum extremal surfaces. So the reason is that even if these two are related to one another with some small energy perturbation, it doesn't necessarily mean that HR is the same for this one and for that one, since the quantum extremal surface is state dependent. So let me illustrate this. So we have some region R, we have some quantum extremal surface for rho R, and then maybe we have some, by acting with some operator, we change the state, which means that the quantum extremal surface could move a little bit. So maybe the new quantum extremal surface, let me make this a little bit bigger. Maybe the new quantum extremal surface looks like that. So this is the chi R for sigma R. And this is chi R for rho R. And now we have a problem, because we can't actually make sense of this thing because these are not density matrices on the same Hilbert space anymore. Right? Sigma R is now on this, whereas rho R is on that. They're not comparable in any way anymore. So we immediately see that the first step in the Dong-Harlow wall argument is going to fail already. We can't use JLMS to make this argument here. They're not quantum states, they're not density matrices on the same Hilbert space. So this is not the same, so we have rho R, sorry, this is rho HR, and this is sigma HR. So this is rho HR. Rho HR is the density matrix on this larger subset, and this sigma HR is the density matrix on this smaller subset. So they're not the same state, and they're not even acting on the same Hilbert space. So these are density matrices. These are partial traces. So it's like in the CFT we can talk about the density matrix on R, and we can talk about the density matrix on R prime. But we can't compute the relative entropy between these two because rho R is acting on the Hilbert space of states restricted to HR, and rho R prime is acting on states on HR prime. So these are not the same. They're not acting on the same states. We can't talk about this quantity here.
Don't you think like there's a part of some bigger Hilbert space?
Yes, they're both part of a larger Hilbert space. But so if you wanted to somehow say I'm going to extend this and talk about the entire bulk, then you could compare them for sure. But of course, the whole point of this is to see, is there a subregion duality here? We don't want to need the rest of the bulk, because once we do, then we've given up on this notion that this entanglement wedge is something that's dual exclusively to this particular subregion here.
Can you just repeat, why is this a back reaction induced problem? Why was this not an issue with JLMS?
So this is an issue of the quantum extremal surface moving. And the quantum extremal surface is not going to move at FLM because that's a classical extremal surface there. We have to work in an order where the quantum extremal surface is different from the classical, where we actually need to worry about quantum extremal surfaces.
So I thought you missed this. So that argument was using HRT?
Yes, FLM is HRT with the first order quantum correction. So the surface is still classically extremal. So it doesn't depend on the state of the quantum fields. Here, as soon as we start using quantum extremal surfaces, this thing starts to change, and then we start to have a problem. Yeah. Okay. So now we could evaluate. Maybe let me further address the question. We could define a state sigma tilde HR, which is trace of this entire. So we can trace out everything out here and define the state sigma on this larger object over here. But that's not, if talking about distinguishability there is not going to help us because that's not the actual entanglement wedge of the state once we're in sigma R. So that's not a way out for us here. So that essentially seems to mean that if we turn on an operator, so maybe I'll draw this much bigger. So this is our R, and this is our chi R for rho R, rho HR. Suppose we turn on some operator here.
So at this point, I think you need to, despite what a quantum operator is, gravitational addressing, navigating your own concept instead of just an insertion of local.
This is true. So we can there's no gauge invariant way for us to talk about local operators in this context. So one thing that we can do is find some way to make this gauge invariant by attaching it to a gauge invariant construct. There are many ways to do this. You could imagine firing a geodesic from this to the boundary, and that makes it gauge invariant. You say, okay, I'm going to as a
What do you
geodesic.
mean by firing this to the boundary?
Well, I mean, specifying this object here using a geodesic. So we say we're going to consider a geodesic from the boundary. It propagates in at some angle. It has some amount of affine parameter, amount of distance that we travel along, and that's how we say at the end of that there is some operator here that takes some value. So this is one way that we can gravitationally address an operator here.
Is that by adding an orbital Wilson line?
Yes, exactly. It's a Wilson line, essentially. We can also, so there are other ways of doing this. I'm not attached to any particular one. You could imagine this being on some kind of a, attached to the extremal surface in some way, which is less well interpreted in the CFT, but still makes a gauge invariant. Yeah, this will not dramatically change our story, but you're right that there's a subtlety here that we need to be careful about what we mean by a local operator in the once we start including back reaction, because it's not specifying a local operator becomes impossible to do in the gauge invariant
It's
way.
not local.
That's right. It's just not local. By adding this line here, we've made it not
If
local.
you make it the boundary, it becomes.
Yeah. That's right. It's an extended. It now is an extended object. Yeah. So suppose we've turned on this extended object, and as a result of this, what happened is the state of the bulk quantum fields has changed, and we have a new quantum extremal surface. This is sigma R for, this is chi R. For rho sigma R. And as a result of this change, we no longer have this full operator in the entanglement wedge. So now let's say we want to reconstruct 5x, well, it's not an entanglement wedge of this state. So let's say this is rho, sorry for saying, not very well. So our HR has changed, and as a result, we can no longer reconstruct this because it's not an entanglement wedge anymore once we've turned on the operator. So we seem to have ourselves a bit of a problem here. We turn on an operator because we want to reconstruct it, but as soon as we've turned it on, the quantum extremal surface has moved, and now we can't reconstruct it anymore. So this is a problem.
Why are you saying that it moves downward or into?
So it doesn't have to move downwards, it's just it can. And once it can, and the fact that it can do that means that we could have a problem here. And I'll give an example shortly where it does do that.
So the solution is that it's not that it never does that.
Yeah, the solution is not that it never does that. Yeah. And again, I'll give an example in a minute where we can see that it doing that. Yeah.
So can but does not need to include the space-time point where the operator is inserted?
So it doesn't need to include. So this homology hypersurface doesn't have to include that. Once we've turned it on, we've modified the space-time in some way, and that means that it's not necessarily the case that this new quantum extremal surface includes that. It will move. Of course, we might be lucky. Maybe it will move to be actually a larger region, and there's no problem. Maybe it moves to be a smaller region, but we'll still include it. But there's always the possibility, and I'll illustrate an example in a minute, that it will move to not include that anymore. And then we have ourselves an issue. So, say a couple more things before I move on to the example.
Netta, can I ask you a question?
Yeah.
So what is the meaning of sigma in the language of the boundary control field theory? Is it a thermal state?
So sigma is, we imagine this corresponds to some low energy perturbation of the state rho in the CFT, and then you just reduce it, you take the trace over R bar of that perturbed state. That's the meaning of sigma r.
The reason that I'm asking is in the lectures of Ahmad, there was always this thermal bus coupled to the AdS2 black hole and so on. So, but here I don't see any trace of that.
No, this is a much simpler setup. We're not coupling our AdS system to anything. We are just standard AdS boundary conditions. The CFT is evolving unitarily. There's no auxiliary system. Everything here is much simpler than the evaporating black hole. So this is easier to understand, not harder. Okay, let me be a little bit more explicit about a couple things. So the fact that we can't reconstruct this in every state means that we have, again, the appearance of state dependence. So whether we can reconstruct a given operator or not depends on the state that we start out with and the state that we end up in once we turn on the operator. So in particular, if we are in a situation where we have two quantum extremal surfaces corresponding to two different states in our code subspace, if we have an operator, if we turn on an operator, I'll address it if you want, phi of x here, and this is the operator we're interested in reconstructing, then we can reconstruct it in either one of these two states. So if phi of x is in the domain of dependence, the entanglement wedge of HR in the sigma state and in the domain of dependence of HR in the rho state, then we can reconstruct it no problem. But if we have phi of y, which is here, then lives in DHR rho, but not in DHR sigma, then we have a problem. So
when I talk about, so you have this
pressing,
Mhm.
and do it to the right.
Yeah, this is one of the reasons I prefer to address it to the relevant quantum extremal surface, because then there's no trace of the operator whatsoever in the wedge you want to reconstruct.
Yeah.
Yeah,
Because you could have done it the right.
Yeah, exactly.
It's a different operator.
It's a different operator, yeah. But there exists an operator where you can't do this for. We don't, certainly there are operators we can reconstruct, and that's fine. But the problem is that there are operators that depend heavily on which state we're in. Now, we could say, just take this code subspace, these are the sets of states that we're allowing ourselves, and make it really, really small, right? We're going to take a code subspace of states that basically never moves the quantum extremal surface. It moves it only to such subleading orders that it doesn't matter. We could do that, but first of all, we can't shrink the code subspace to 0 size. Can't do that to be one-dimensional, because then you can't act with operators. So that's not going to be a solution. So you could say, you know, possible idea, shrink the code subspace. But the problems, first of all, can't shrink to 0 size, 1 dimension. Because then we can't act with operators. We can't act with an operator and ask how do we reconstruct this, because as soon as we act with an operator, we need more than 1 dimension in our space. The second is that we'd really like to be able to talk about black holes. We want to be able to take an operator, a heavy operator, act with it, form a black hole, do reconstruction. We want to be able to do that. So the most interesting code subspaces are large. So what do we do? And the answer is we kind of have to learn to live with it. So we have to be able to understand how much of the bulk can we reconstruct within a given code subspace in a state-independent way, and how much of it is just going to be state-dependent, and it really depends on which operator you've picked to turn on and which state you end up in. And then we can say we have a robust understanding of the part of the bulk that we can always reconstruct within a given code subspace, and everything else is state-dependent. And that puts us in some sense on a firm footing as far as what we understand and what we don't understand. We know that at least there's a part of the bulk that we can always reconstruct, and it does turn out to be larger than the causal wedge. So what is this part of the bulk that we can always reconstruct within a given code subspace? Again, it's important that we talk about the code subspace rather than asking what is the part of the bulk we can always reconstruct, because if you don't talk about a code subspace, you're literally considering all possible bulk geometries. Because you can just form a black hole from a neutron star and so on. And there's no sense in which there's one operator, any one operator, that lives in all of them except the identity. Okay, so this is something called the reconstruction wedge. So the idea here is to ask, what is the worst case scenario that we can always reconstruct, like the worst state in our code subspace? What can we always reconstruct from the worst state? Does there exist a worst state? Is it going to be a situation where, and this state might reconstruct that, another one might reconstruct this, and another one might reconstruct this, and another one might reconstruct that, and there isn't a worst state? They're all excluding sort of different parts, or is there some kind of an envelope where we can safely say everything in this envelope is reconstructible, and there's some state for which this envelope is the entanglement wedge? So that second case would be much nicer, because then we can always identify that state, find its entanglement wedge, safely do a reconstruction state-independent way within the code subspace. Fortunately for us, it turns out that this is indeed what happens. Rather than having an outer envelope which is just some intersection of the wedges and isn't a nice wedge on its own, it does turn out that this outer envelope is in fact an entanglement wedge of a particular state in the code subspace. So this is work initially by Pennington and by Hayden-Pennington. And further clarified by Akers, Leichenauer, and Levine. they actually, these folks actually coined this term, but Patrick and Jeff were the ones who sort of came up with the first issue here. So Hayden and Pennington, in a very beautiful paper called Alphabets, the alphabets of black holes, they said that you can always do state-independent reconstruction in the entanglement wedge of the maximally mixed state of your code subspace. So what that means, what they're saying is, and they argued this based on quantum information theoretic arguments. This is alphabets, black holes. Essentially, what this means is you take your code subspace, you define some code subspace, you say this is the set of states I'm interested in reconstructing operators that relate these two states to these different states to one another. And then you ask, within this code subspace, what is the maximally mixed state? I don't mean maximally entangled pure state, I mean the maximally mixed state. Now, some of you in the audience might be thinking, well, for in a quantum field theory, technically speaking, the maximally mixed state isn't really well defined. This is true. They were working in this approximation where we're talking about quantum information theoretic quantities, and so we're working with a finite dimensional Hilbert space, and the maximally mixed state is well defined.
Just the identity.
Sorry?
Have proportion to identity.
Yeah, proportional to identity, yeah, exactly. Now, in general, in quantum field theory is a little bit more of a question, what do we actually do here? So one thing that seems to work is if there's any notion of a thermal state in your system, to talk about the entanglement wedge of the thermal state.
So the infinite temperatures.
Yes, that's right, yeah. So that seems within quantum field theory, if we're actually treating the system at this level of type 3 phenomenal algebras, that seems to be the thing that takes the place of the maximally mixed state in this alphabets proposal, yeah.
So in this state, this means that if they add another operator, the wedge will not shrink anymore, the wedge will stay fixed?
So within the code subspace, if you're only acting with an operator that maintains, that stays within the code subspace, then the entanglement wedge is not going to shrink further. You're not guaranteed that it's not going to grow a little bit.
Yeah.
It could grow, but it's not going to shrink further. That's why this is, thank you for the segue. This was shown by Akers, Leichenauer, and Levine, that the entanglement wedge of the maximally mixed state is the smallest, outermost entanglement wedge.
So it's like you don't want to talk about complexity, perhaps.
I will talk about complexity in a bit, yeah.
So it's like the maximum complexity state?
Absolutely not. It's the minimal complexity state, as it were. The least complex state. And it's the smallest, so if you want to think of probing deeper into the bulk as being more complex, you would want it to be the case that the smallest wedge is the least complex one. So indeed, this is what happens. In reconstruction, up to the outermost quantum extremal surface is simple. Beyond that, it's complex.
So this is particularly a mixed state we're not interested in.
Is it uninteresting?
No, we discussed low energy state, low temperature state.
Good, actually, yeah. So
why then? We're discussing infinite temperature states, and also you're assuming that there exists such a thing. We have a Hagedorn spectrum, for example.
I completely agree with you. So the key thing here is this is the maximally mixed state within your code subspace. You take the most mixed things that you can get. And it may not be, for example, proportional to the identity either, depending on which states you have. So
Tricky. I that's just finite dimensional.
That's what?
It only makes sense for a finite dimensional.
So Yeah, the maximum mixed state only makes sense for finite dimensional Hilbert spaces. So as soon as we're trying to work within quantum field theory, and again, this is all based on quantum information theoretic and quantum coding arguments, so this is good in finite dimensional Hilbert spaces. If we want to work with infinite dimensional Hilbert spaces, then every time we work with them, for every problem we do, we have to ask ourselves, what's the correct avatar of this in this system? And it takes some work and some intuiting to figure that out every time. So I'm going to try to give an example. Maybe I'll try to do it now. Yeah. So yeah, let me give an example of a situation where we're doing quantum field theory, and we end up working with essentially end up working with the thermal state.
At what temperature?
So we have a black hole. The black hole is at some particular temperature, and it's at the temperature of the black hole. Yeah. Well, it's a black hole at equilibrium, and it's at the temperature of the black hole. Yeah. Yeah.
There was, in my understanding, some freedom in your definition of the subspace. Does this Aidan Pennington statement depend on a certain definition, or is it true for any?
So code subspace will, I mean, they use the notion of code subspace. That's basically you take some subspace of your Hilbert space, and you don't have to define this using an energy band in particular. But you do want, so their theorem is quantum information theoretic, so they don't need to have a semi-classical bulk dual. But we'd like to consider states with semi-classical bulk duals in the code subspace. That said, they don't have to have the same geometries at all. So you could have a situation where you have two states in the code subspace. One of them is a black hole formed from collapse, and the other is an eternal black hole. And they are obtained from one another essentially by looking at a very large code subspace. So you're looking at all of the microstates of a typical state black hole. Then what you have is the situation is you have all of the ways in which the black hole is formed, and the maximally mixed state is essentially going to look like Schwarzschild. So that's a good example. Let me go over that instead. So suppose we have a pure state, a black hole formed from collapse. We have some pure microstate of a black hole. So this is it, and we have a code subspace of one dimension. It's just this pure state. Okay. Now we want to. So this is a single microstate, pure state. And now we say, okay, we want to do reconstruction, but we want to be very ambitious. We want to consider the typical microstates, actually, typical black holes. Now, typical black holes have e to the a over 4g, or e to the s Bekenstein-Hawking entropy and microstates. So we want to say, all right, we want to be able to act with any operator. We want to be able to consider all possible microstates. And then we're going to ask. So we're starting with, say we're at some Cauchy slice of late times here. And we'll ask, okay, we want to be able to act with the operators here. We want to be able to not act with operators. We want to just ask what are all of the, what's the reconstruction wedge of a typical black hole? And with the knowledge that this is the size of the Hilbert space. And the answer is, well, you're going to take the maximally mixed state, or in this case, it's going to be the thermofield double, one side of the thermofield double in this black hole. And you say, okay, what does that look like? Well, just from the perspective of one side, that looks like this. And so the reconstruction wedge of a black hole, where there's this typical state black hole, you have all of these microstates, and you want to ask, what's the reconstruction wedge? What can I reconstruct in a way that's totally state independent? If your black hole looks like Schwarzschild, essentially, if the maximum mixed state looks like Schwarzschild, then you have the thermofield double, and this is the reconstruction wedge of that. So this is essentially an illustration of how you start from this situation where you have a single pure microstate. There's no quantum extremal surface here. You can reconstruct the entire bulk to a situation where this is actually the reconstruction wedge over there. Now you could say, how do you get to the point where you start out with something like this and you end up with something like that? there's no quantum extremal surface over here. In what sense is this even a reconstruction wedge for this space-time over here? In what sense is this the outermost quantum extremal surface for this when there's no quantum extremal surface here at all? Right? This looks pretty confusing. And in fact, one way to see this, it's kind of cute. You say, okay, I'm going to turn on an operator over here. Right? Reconstruction means I have to turn on some operator over here. And say I want to reconstruct it. Well, okay, if you want to reconstruct this operator, now we've turned on an operator in here. We need to look at code subspace that at the very least is going to include some span of states that allow us to modify the state straddling the event horizon. So.
Why straddling?
It could be out here. It's well, if it's out over here, then there are various geometric arguments you can use to say, oh, but this is a black hole, a stable black hole, so it roughly looks like this. But if it's inside, then you say, okay, it really is not going to look. You can sort of trace an old geodesic back here. You're going to get to r equals 0. Here, you're just going to say, well, I get a singularity, or you get a second asymptotic boundary. So I find this to be more confusing than trying to reconstruct one up here, which is just a causal wedge. So we turn this on, and that means that we need to, you can imagine sort of freezing. We have these ingoing, outgoing modes that are right movers inside and outside the horizon. We can imagine freezing out the state over here and over here, but we have to allow ourselves some span of states here if we want to be able to turn on an operator.
Why is that span of states outside the horizon?
It doesn't have to be, but it's significantly more convenient to allow it to be outside the horizon if we want to take this to be arbitrarily close to the event horizon. We don't want to worry too much about this support being trans-Planckian, so we want to give it some support outside if we need to. Okay, so then what happens is we say, all right, so we're considering some span of states, and then we need to talk about the reconstruction wedge. We need to ask, what's the most mixed state in this code subspace? And that, essentially what that boils down to is disentangling. So here in this situation, you might imagine that this is like an EPR pair. It's maximally mixed with each other. They're maximally entangled. But of course, you can't have a system that's maximally entangled, these two being maximally entangled, and also being maximally entangled with a third system, which is what we're looking for. So what you have to do is you have to disentangle these Hawking modes in order to figure out what the most mixed state is over here. And as it happens, as you disentangle these, then you're in a situation where, okay, I've disentangled these modes. Now I don't have the normal entanglement structure of something that looks like a local vacuum. And the consequence of that is you end up with a shock wave somewhere you end up with a shock wave through here. It modifies your geometry in the past. And the modification of that geometry in the past actually results in a quantum extremal surface. So there's a lot of back reaction as a consequence of a small modification here of disentangling these modes up here. Then you evolve them backwards in time, you get a lot of back reaction. Some would say you get a firewall.
Because the energy, as you go back, is bigger.
That's right, yeah. Everything is blue shifted as you're going backwards. You get a lot of back reaction, and you can actually find there's a quantum extremal surface here. And that essentially corresponds to this quantum extremal surface over here.
What would you say you have?
What is that?
You said somebody say you have a firewall. What would you say you have?
Well, so it depends on how it depends, right? Here we sort of want, we found it, so I should say you can find this derivation in a paper I wrote with Jeff Pennington and Arvind Shapati-Mogadam. In that paper we said we consider a code subspace of states with a smooth horizon. At least over here. Now, of course, it's possible that by doing this, you've messed with the structure of the horizon at earlier times. But I guess I would say if we're in a typical state black hole, I would say we have a firewall. I might take that back in a couple of years, but for now, I'll say that's my best guess. Yeah.
So in this example, it goes back to the causal wedge, right?
So
this is the causal wedge.
So in the case of if you're exactly in Schwarzschild, you don't have any. If your mixed state is exactly Schwarzschild, this will be the causal wedge. But this is not always the case. Yeah. Again, we took a huge code subspace here. We took all of this. If we had said we're not considering all, we're not so we're the typical black hole where we don't know the microstate, and so we just have to consider all of them. If you say I'm considering some span of microstates, then you can certainly reconstruct the interior, parts of the interior at least. Yeah. Yeah.
Let's say the code subspace is defined through like the energy of the operators you're allowed to apply or something like that. So how do you imagine the reconstruction wedge to look like as function of this energy cutoff?
Right, I'm sorry. This last bit.
How do you imagine the reconstruction wedge to change this function of your energy cutoff? I mean, when you go all the way to the energies of the black hole, you get only the causal wedge.
So in general, the reconstruction wedge goes deeper than the causal wedge. It's just that in this particular example here, it depends on how large your code subspace is. So if you consider all possible semi-classical geometries in your code subspace, then your reconstruction wedge is going to be very close to the empty set. Maybe just like a sliver around the asymptotic region. Now, if you consider your code subspace to be the black hole microstates, it's going to be basically the causal wedge. You consider your code subspace to be some small perturbations of Schwarzschild of the Vega black hole, then your space is probably going to be most, probably not all, but most of the space time. So it's really code subspace dependent, which is not the same as state dependent, of course.
I think I missed something. When you say you raised the question before that you can reconstruct by taking the relative entropy.
Yes.
Did you answer that?
Well, so I said the reason you can't reconstruct using the relative entropy is precisely because you simply cannot do this reconstruction in general. You just can't, right? That you can use an argument similar to the relative entropy argument in the reconstruction wedge, but you can't do it in general because, and we see that you can't reconstruct in general. We can't use that argument in general. So I didn't solve it because it's not solved. It's not a question that we're trying to solve. We figured out that it can't be done.
But even if the perturbation remains inside the wedge.
Yes. Oh, then we can. Then we can do it. So there's a nice argument by Yiming Chen for doing, I guess, a few others for doing reconstruction when the quantum extremal surface moves, as long as you're reconstructing things within the reconstruction wedge. You can sort of already see this. So this argument here said, if this state is here, then we can do a reconstruction. For the purposes, if you want to think of it in terms of the relative entropy, you could say, oh, well, I'll just take the state up here and imagine, I can reduce it to this region. And then I can talk about the relative entropy of the state that was originally defined here and the state that I've now reduced to this region. So this operator, as long as this operator is defined in all of the states that I'm interested in, then I don't have a problem. Let's see, I have 15 minutes, so I feel like I should maybe switch gears. Now that we've uncovered, this is a sort of, in some sense, the state of the art on where we are on reconstruction and the complications that come up. Of course, I've glossed over a lot of things, but hopefully provided you with the references to look them up. I want to say a few words about, well, I could say either a few words about the evaporating black hole. Let me say one or two words about the evaporating black hole, and then I'll talk a little bit about reconstruction complexity. That was part of the title, so I should say a few words about it. So for the evaporating black hole, you might say,
what
yes?
do you mean exactly by reconstruction? I mean, you are now talking about asymptotically flat black holes.
Absolutely not. I'm definitely still talking about AdS. So when I say, if you're worried about the black hole evaporation in AdS, we're going to couple it to a bath. Now we're going to couple the black hole to a bath. So that's what I mean by the evaporating black hole. So what Amit talked about last week, I assume. So in the case of the evaporating black hole, you could say, okay, what is the reconstruction wedge? Do we have to worry now? So I'll jog your memory a little bit. So here we have an evaporating black hole. Bath. And you could say, okay, well, Amit's told us, I hope Amit told you, that at some point in this black hole evaporation process, maybe this was born in some shell, at some point in this black hole evaporation process, there's a non-trivial quantum extremal surface that forms, and that new quantum extremal surface gives you the downturn in the page curve. Did Amit say as much? Yes, okay, great. All right, so then you could say, okay, well, we've then used this to say, okay, this is the quantum extremal surface for some some time slice here on the asymptotic boundary. And we've also said, okay, that because the CFT plus the bath is in a pure state, that means that we should be able to identify the entanglement wedge of the radiation as this region that's behind this, together with, so what we should identify this as the entanglement wedge of the radiation. And the reason that's of course very appealing is because that tells us that after the page time, we can reconstruct the black hole interior from the radiation, which is of course what we want for black hole evaporation to be unitary. Now you might say, now this is worrying because what if this is not in the reconstruction wedge? In the specific examples that we worked out in 2019, we were actually talking about the maximally mixed state. We're talking about Hawking radiation, which is a thermal state. So we actually were in the maximally mixed state of a code subspace of this particular black hole. So at least in these examples, we are safe. This is the reconstruction wedge. Now you could ask, what happens if I now decide that I want to talk about the microstate, decoding the radiation of a typical black hole? Then you have to start asking, is this still the reconstruction wedge? And well, that essentially boils down to the firewall problem. Are we able to is the interior emergent from the, of a typical state black hole? Is it emergent from the radiation? Can we decode it? Question mark. For everyone here. Sorry?
It could be a fuzzball.
It could be a fuzzball, it could be a firewall, it could be a lot of other things. This is work for all of you to take up in the coming days.
But whatever it is, there is no GR black hole in here.
Yeah. Well, certainly not this geometry.
Yes.
Okay, so I just wanted to make a brief comment on this since I alluded a little bit to black hole evaporation throughout. Now, this actually gives me a good segue to the 10 minutes of complexity that we're going to get here. So this protocol, we called it the dual of Hayden-Preskel, or the geometric realization of Hayden-Preskel, because the information from the interior sort of made its way out here. But there's a companion to Hayden-Preskel, which is a paper by Harlow and Hayden. Hayden-Preskel tells you that you can decode the radiation, assuming making certain assumptions about the black hole evolution, basically that it's unitary and looks to first or second approximation like a random system. And then Harlow and Hayden said, yeah, sure, maybe you can certainly decode it, but it's going to be really, really hard. So Harlow and Hayden said essentially that the complexity of reconstruction, of decoding the radiation, is exponential in the black hole entropy. Now, when we say complexity here, you can, I don't have time to go through the thorough definition, but you can think of it as if you have a quantum algorithm that you want to run, where you're given the radiation, and you want to produce a distilled state of some diary that fell in, then that algorithm, you could ask, if I have some fundamental set of gates in that algorithm, maybe unitary 2 gates or something like that, you could say, how many of those gates do I have? And how does it scale with the number of qubits of the system? So if it scales exponentially with the number of qubits, then we say that this is a very high complexity system. Scales polynomially or sub-exponentially, then we say it's relatively simple. It's 2 different complexity classes. Now, so Harlow and Hayden argued.
Before you discuss black holes, if I take a piece of coal, what does it the same phenomenon occur? I mean, presumably it gets harder and harder, but is it
Sure.
exponentially?
Yeah, that's right. That's right. So in the principle, you could say this is no different from a lump of coal. The main difference between a black hole evaporation and a lump of coal is that the black hole has 2 different descriptions. It has a nice effective description. I say a lump of coal, a burning lump of coal kind of doesn't have a nice effective description, which is useful for us. That's the main, I would say that's one of the differences here between a lump of coal and a black hole. So this is sort of our segue into this. We can ask, how do we geometrically see that that reconstruction of the black hole interior is hard from the radiation? In what sense is it geometrically and qualitatively different from reconstruction of this region from the dual CFT? What makes these different? And the answer is a very beautiful story about non-minimal quantum extremal surfaces. So we've been focused on these distinguished quantum extremal surfaces that are the ones with the smallest generalized entropy in their class. But what about the non-minimal ones? So non-minimal QESs and complexity. So this story goes back to 2017 in a paper I wrote with Aaron Wall, where we proposed that the area of a non-minimal extremal surface, later this was generalized by Rafael Lusso and friends to quantum extremal surfaces, that the generalized entropy of a non-minimal quantum extremal surface actually computes an important quantity in the CFT. It's a coarse-grained entropy that we call the simple entropy, rho r. Now this is not just any non-minimal quantum extremal surface, it's the outermost one. So this is the outermost quantum extremal surface. The same one that appears, it appeared earlier. Here we're again interested in its outer envelope, the outermost quantum extremal surface. So the generalized entropy of the outermost quantum extremal surface computes this coarse-grained entropy. This coarse-grained entropy is a maximization of the von Neumann entropy over all states rho r that live in some set S, where the set S is defined in the following way. These are all the states or the density matrices on R whose low complexity observables are identical. And I mean low complexity in that sense. So basically, if you didn't have the ability to compute high complexity observables, then all of these states would look identical to you. And so among all these states, we ask what is the one with the largest fine-grained entropy. And we call that the coarse-grained entropy of our original, let me call this name.
This maximization is well defined.
Sorry, what was that?
This process is well defined.
It could be a supremum, not a maximum.
Yeah, no.
Yeah, it could be a supremum. Yeah.
I mean, can you speak about the states with the low complexity observables? Is something that is well defined in the.
So in quantum field theory, you run into a bit more of an issue. There we have to make the leap, the assumption that low complexity means that there exists that it's possible for it to propagate causally in the bulk, rather than something that sort of turns out to be totally non-local in the bulk. So there is an assumption that goes into that if you want to make sense of it in quantum field theory. You can argue that this is well defined when you talk about infinite dimensional Hilbert spaces. Yeah.
Before, when you defined the relative entropy, you did not take the generalized entropy, you take ordinary.
That's right, that was different. Yeah, yeah, that was a different definition, different quantity.
Low complexity observables mean just pilots or pilot number of operators.
That's an example where, so low complexity here, we really mean sub-exponentially complex. So not just polynomial. So we're allowing them to be a little bit more complex than polynomial, but it can be exponential.
Complex, you mean the number of insertions of operators of the crowd state.
Yeah, that's right. Yeah. So that's
And what kind of operators?
Well, you can imagine local operators.
Sure
Surely there's more. In certain cases, yeah. Let me leave it at local operators, and I'll see if I can come up with other examples while I talk for the remaining 5 minutes. Okay, yeah, one more question.
Given definition of complexity in QFT, to define this maximization, you necessarily take the thermodynamic limit?
Is this what last?
To make this maximization,
yeah.
You necessarily take some sort of thermodynamic limit to distinguish between low and high complexity?
Yeah, so I mean, let me finish this, and if I can answer your question, if it doesn't, ask again. Okay. Okay, so this is the basic, so we have this story relating telling us essentially that the outermost quantum extremal surface is essentially the entanglement wedge of the simplest state, of the state that you would be you would think you have if you only had access to simple observables. So you could say, okay, well that suggests the reconstruction up to the outermost quantum extremal surface is simple, and behind the outermost quantum extremal surface is highly complex. And this is essentially the complementary story of the Python's lunch, which is about reconstruction. So I'm going to state the strong version of the Python's lunch. So this was pioneered by Adam Brown and others in the sort of this one direction, and the second direction was in this paper that I wrote with Jeff and Arden. And the statement is that the only source of exponential complexity of reconstruction is non-minimal quantum extremal surfaces. And indeed, the reconstruction behind a non-minimal quantum extremal surface, the complexity of reconstructing an operator behind the non-minimal, the outermost quantum extremal surface, QES, is given by, I'll write that and then I'll finish. So draw a picture and then I write down the equation. So on a moment of time slice, if we have compact surfaces, then we have the asymptotic boundaries of this fork factor. We have the outermost quantum extremal surface. So this is a moment of time slice. I'm just drawing it in 3D instead of 2D as I've done so far. Then there's going to be some smaller quantum extremal surface, which is the actual minimal one over here. And you can prove that between them, there's a maximal quantum extremal surface. So this is a geometric argument that you can show. We call this the bulge of this thing. And so the complexity of reconstructing between this chi over here, which I'll call it chi 2, this is chi 1, this is the minimal one, this is the outermost one. If you want to reconstruct between them, the complexity of that is proportional to this quantity. Gen chi 2. The difference in the generalized entropies between this surface and that surface. That's what it takes to reconstruct operators again. Yeah, there's a 1/2 in there. It comes from the consideration. Okay, I'm actually not 100% sure that I agree with this 1/2, but it comes from considerations where, in the case of the evaporating black hole, after the page time, there is a non-minimal quantum extremal surface for the radiation. That's essentially this one over here. And in order to correctly reproduce Harlow-Hayden, you need that factor of 1/2 over there. So that's where the factor of 1/2 comes from. Okay, I think I'm over time, so I will finish here. And again, I think I provided the references. I'm sorry the complexity bit was so short. Thank you for your attention. Tonight? Yeah, sure.
Okay, very good question.
Indeed.
So I promised a repetition. So for those of you who may have come later, please, for the Einstein tour, please go look in what group you are and
There's a
arrange
list
accordingly. They have the
downstairs.
list downstairs. It says one would be at around 3:30 and the other around 4:20. Thank you. And so let's thank Netta again.